welcome to This Explainer. Today, we're taking on a challenge that I know trips up almost everyone who's ever shopped for a new computer, a smartphone, or even just tried to pick a decent home internet plan. We're looking at the dreaded spec sheet. You know the ones? They're just packed with this alphabet soup of acronyms. MBPS, MBPS, GHZ, TBPB. Honestly, it can look like a completely foreign language, kind of like it was intentionally designed to confuse us. But don't worry, by the end of our time together today, you're going to be completely fluent. We're going to translate these dry tech measurements into practical, real-world knowledge so you know exactly what your devices are doing behind the scenes and, more importantly, what you're actually paying for.
So here's our roadmap for today. 1. The building blocks. 2. Sizing up storage. 3. Understanding data throughput. 4. Processor speed explained. And finally, 5. Pushing CPU limits. Let's jump right in.
Section 1. The building blocks. The foundation of digital logic.
The absolute foundation of all computing is the bit, which is just short for binary digit. It's literally the smallest unit of data possible, representing a super simple fundamental state. It's either a 0 or a 1. Think of it as a microscopic on and off switch. And since computers operate entirely on binary logic, absolutely everything your device does is governed by these bits. Every single pixel of that high-definition movie you're streaming, every fraction of a second of your favorite song, every single keystroke in a massive video game, all of it is ultimately broken down and represented using practically infinite combinations of these raw 0 and 1s.
Now, a single bit by itself, well, it can't really tell us much. It's just on or off. But when we group them together, things get really interesting. A byte is a unit of data that consists of exactly 8 bits. And because each of those 8 bits can be either a 0 or 1 independently, a single byte gives us 2 to the power of 8 possible combinations. That's 256 unique values. This gives the computer enough variety to actually start storing real characters and meaningful information. For example, in the standard ASCII encoding scheme, the capital letter A on your keyboard is stored exactly as 01000001 in binary. So one letter equals 1 byte.
The absolutely crucial point here is understanding how these two terms are used in the real world, because tech companies use them very, very differently. Bits with a lowercase b are generally used to measure data transfer rates, like the internet speed you buy from your ISP. Think megabits per second, or Mbps. Bytes with an uppercase b, on the other hand, measure data storage or actual file sizes. Think of a 500 gigabyte hard drive. This right here is precisely why a 100 megabit internet connection doesn't download a 100 megabyte file in 1 second. You always have to account for the mathematical difference between the two when you're looking at specs.
Moving along to Section 2. Sizing up storage. Scaling from kilobytes to petabytes. As our files get bigger, we start using standard multipliers. A kilobyte, or KB, is roughly 1,000 bytes. A megabyte is 1 million bytes. A gigabyte is 1 billion bytes. A terabyte is 1 trillion bytes. And if you're dealing with massive enterprise servers or huge cloud data centers, you might even deal in petabytes, which is 1 quadrillion bytes. Now, a quick aside, just remember that in a strict binary system, the multiplier is actually 1024. Not exactly 1000, but these nice round numbers are how storage is marketed to us as consumers, just to make the math easier to digest.
I really want you to think about the sheer mind-boggling scale we're talking about here. When you go buy a standard 2 terabyte hard drive at the store, you're holding a physical object in the palm of your hand that can store approximately 2 trillion bytes of data. That means 2 trillion separate groups of 8 individual on and off switches, all packed into a tiny little piece of metal and plastic. It's pretty wild.
Let's put this into perspective with a little math from our sources to really demystify this. Take a relatively tiny file, let's say an 8 megabyte photo on your smartphone. First, you multiply 8 by 148,576 to get roughly 8.3 million bytes. But remember, every byte is 8 bits. So we multiply that by 8, and we realize that a single 8 megabyte file is made up of exactly 67,108,864 individual bits. That is over 67 million zeros and ones, just to show you a simple picture of your cat.
All right, Section 3, Understanding Data Throughput, Data in Motion.
Throughput simply refers to the rate at which data is successfully transferred from one point to another over a given amount of time. It's essentially the lifeblood of network performance and disk read and write speeds. Mathematically speaking, throughput equals total data transferred divided by the time taken. It's basically the miles per hour of the computing world, telling you exactly how fast your data is actually traveling from point A to point B.
Let's run a real-world calculation together so you can see this in action. Say you need to transfer a 10 gigabyte video file, and it takes exactly 500 seconds to finish. What is your actual throughput? Well, first, we convert those 10 gigabytes into megabytes, giving us 10,000 megabytes. We divide that 10,000 by 500 seconds, which equals 20 megabytes per second. Notice that's with a capital B. But what if you want to know what that requires in terms of your internet network speed? You multiply that 20 by 8 to convert the bytes back into bits, revealing that your network must be sustaining a throughput of 160 megabits per second, lowercase b.
But as we all know, we rarely ever get the perfect, maximum speed our provider advertises, right? Why is that? Because throughput is affected by several physical and digital roadblocks. Bandwidth is the absolute maximum data rate your system can support. Think of it as the physical size of the pipe. Then there's latency, which is the delay between sending and receiving. Network congestion is exactly what it sounds like, competing traffic slowing you down, very much like a severe traffic jam on the highway during rush hour. And protocol overhead refers to the hidden data used for things like headers and error correction just to make absolutely sure your file arrives safely. All of these factors combined chip away at your actual real-world throughput.
Next up, Section 4. Processor Speed Explained. The brain of the computer.
So, processor speed, commonly known as clock speed, measures how many cycles a CPU can perform in one single second, and we measure this in hertz. But what actually happens in one of these microscopic cycles? Well, during a single clock cycle, the CPU performs 3 distinct steps. It fetches an instruction, it decodes what that instruction actually means, and then it executes it. That full process, that's one cycle.
Modern computers are, quite frankly, terrifyingly fast. When you see a spec sheet advertising a 4.2 gigahertz CPU, remember that the prefix giga means billion. So that processor is executing 4.2 billion fetch, decode, and execute cycles every single second. It's just an almost unfathomable level of mechanical speed.
What's really interesting is how these speeds map directly onto your daily life. A 1 to 2 gigahertz processor is super common in low-power devices like smart home tech or just basic web browsing on a phone. 2 to 3 gigahertz, that's the sweet spot for normal laptops doing standard office work and light multitasking. But if you're gaming, doing heavy video editing, or running servers, you're going to want to look for that 3 to 5 gigahertz range. And anything 5 gigahertz or higher is usually specialized hardware or overclocked CPUs meant for heavy scientific rendering or extreme enthusiast gaming.
And finally, Section 5. Pushing CPU limits beyond the GHz metric.
It's time to bust a major myth here. I want you to think about this question. Does a higher clock speed always mean faster performance? If a CPU has a higher gigahertz number printed on the box, is it automatically the better computer? Well, actually, no. The short answer is not always.
Clock speed is really just one piece of a very complex puzzle. A CPU's actual performance heavily relies on alternative factors. For instance, the number of cores allows the computer to multitask and handle different jobs simultaneously. The architecture, or the physical design of the chip, determines how efficiently it executes its instructions. There's also the cache size, which is local memory, and perhaps most importantly, thermal throttling. Heat is the absolute enemy of electronics. If that massive 5 gigahertz processor gets too hot in a super thin laptop chassis, it's actually going to intentionally slow itself down just to keep from melting right there on your desk. So instead of just cranking up the clock speed and generating a ton of system-killing heat, engineers use smart architecture to boost efficiency. 2 prime examples of this are cache memory and parallelism. Cache memory is a tiny, incredibly high-speed memory located physically right next to the CPU. It holds your frequently used instructions. Think of it like keeping your most used tools sitting right there on your desk, rather than having to walk all the way out to the shed, which would represent your main RAM every single time you need a screwdriver. Parallelism is the ability to divide tasks across multiple cores or threads so the computer performs multiple instructions simultaneously, rather than waiting in a single file line.
Now, some enthusiasts try to force their hardware past its factory limits, a process called overclocking. Overclocking means intentionally running a CPU at a higher clock speed than its default factory-tested setting. But this comes with some pretty serious real-world hardware risks. It generates excess heat, which can permanently damage the CPU or trigger that intense thermal throttling we just talked about. Over time, this extreme heat significantly reduces the lifespan of your components. And if the hardware simply can't keep up with the forced speed, you're going to experience severe system instability, data loss, random crashes, the whole shebang.
To cement this idea that architecture matters just as much as raw speed, our source material highlights a really crucial reality. A multi-core CPU may outperform a single-core CPU even if its clock speed is lower. A brilliantly designed team of slower workers can often get far more done than one really fast but easily overwhelmed worker. Efficiency often beats out brute force, for sure.
We've journeyed all the way from the microscopic on-off switch of a single bit to the multi-billion cycle speeds of modern processors. So I want to leave you with this thought. Next time you look at a new internet plan advertising megabits or a computer spec sheet bragging about gigahertz and multi-core architecture, do you know exactly what you're paying for? Because now you actually have the tools to look past the marketing jargon and understand exactly how your digital world operates. Thanks so much for joining me on this explainer, and keep questioning the tech around you.